Hello class, and thank you for watching. In this lesson 1.8 parent functions, you will learn how to identify key characteristics to these parent functions. Now, a parent function is the most basic version of a function, and here are 3 of the 7 examples I'm going to be looking at. Well, except for this one, we're not going to look at this one today, the exponential one, but these are 3 of the of various parent functions. And we're going to be looking specifically at 7 of them that you should have studied in Algebra 1, Algebra 2, and talk about some of those basic characteristics about them. Now, a family of functions is a group of functions with these similar characteristics. Now, each member in this respective family of functions is a transformation of these parent functions. So we have a family of linear functions, we have a family of quadratic functions, and when we transform these basic ones, these parent functions, we create again their quotation offspring functions. So they'll have some of the same characteristics in terms of the way the graph looks, domain and range, and some of those situations, but there obviously be transformations of these parent functions. So let's begin with our first one. The first one is referred to as a linear function, and the parent function for this is the notation y, which is the same thing as f of x. Let me use f of x instead. F of x is equal to x. This is the rule, our parent function. Now the domain for this function is the interval of all real numbers from negative infinity to positive infinity. And the range is the exact same thing. It's all of the y values from negative infinity to positive infinity. As you can see, it has an x-intercept at the origin at 0, 0, and it crosses the y-axis also at the origin at 0, 0. Now this one does not have any extrema. No extrema at all, no maximum, minimum, relative, or absolute at all, because it does not change direction. And the reason for that is because it's increasing from negative infinity to positive infinity. It never decreases. The end behaviors of the function, as you can see, is that as x approaches negative infinity, so to the left, our function is also approaching negative infinity. And as x approaches positive infinity, our function is approaching positive infinity. So again, these two ends are pointing in the respective direction. So to the left, we're pointing towards it's pointing downwards, so towards negative infinity, and the y values are pointing upwards, so they're getting higher and higher and towards positive infinity. It has no discontinuity. This function is continuous. There are no gaps, holes, or jumps of any kind. And this is referred to as an even function. I'm sorry, not an even function. How silly of me. This is referred to as an odd function. Because as you can see, if I flip this 180 degrees, this is going to be symmetrical through the origin. So anything that has, again, a symmetry through the origin is referred to as an odd function. Origin symmetry, or symmetrical through origin. Again, through 0, 0. Okay, then let's move on to the second function. The second function is the absolute value function. The rule, the parent function for this, is obviously going to be the absolute value. So f of x is equal to the absolute value of x. The domain is also all real numbers from negative infinity to positive infinity. However, the range is all of the values from 0 to positive infinity, including 0 itself. Our x-intercept is at the origin, and the y-intercept is also at the origin. This does have an extrema. It has an extrema at 0, 0, which is an absolute minimum. And this function increases from 0 to positive infinity, which is to the left of the extrema. So from 0 to positive infinity, that direction, the graph is going upwards, as you can see. And it decreases from negative infinity to 0. So from negative infinity to 0, again, that's this red one right there, the graph is going downwards, so it's decreasing. The end behaviors, moving on to the end behaviors. Well, as x approaches negative infinity, so to the left, the function is pointing upwards, so the function is approaching positive infinity. And as x approaches positive infinity to the right, the function also approaches positive infinity. Again, the two ends are pointing upwards. Then we have discontinuity. In terms of discontinuity, there is none. This function is continuous. Again, there are no holes, no gaps. And this function right here is referred to as an even function. You can tell it's even because it's symmetrical again through the y-axis. Flipping again the left side over the right side is going to get you again the exact same symmetry. So this is symmetrical through the y-axis. So let me write that down. Let me just erase this. So it's an even function because symmetrical over or through the y-axis. Now I'm going to copy this down because the next function, which is the quadratic function, has the exact same characteristics. With the only exception, of course, is the rule. The function rule for this one, the parent function for this, for all quadratics, is f of x is equal to x to the second power. But everything is essentially the exact same thing. It has the exact same characteristics as the absolute value function. The only difference is that it looks like a u instead of a v. Our domain is from negative infinity to positive infinity. Our range is from 0 to infinity. We intercept the x-axis and the y-axis at the origin. It has this one extrema, 0, 0, which is an absolute minimum. It increases in the same interval from 0 to infinity and decreases from negative infinity to 0. The end behaviors are the same. Both ends are pointing upwards. So to the left, our function is approaching positive infinity, and to the right, our function is approaching positive infinity. It is continuous like the absolute value function. It just doesn't make this sharp turn right here in the corner, and it just again curves upwards. And it is also referred to as an even function because of the symmetry. It's symmetrical through the y-axis. So this is an even function. So let's move on to our next function. Our next function is the cubic function. the rule for our cubic function is f of x is equal to x to the third power. The domain for this function, just like the line, is all real numbers. Like the linear function is all real numbers along with the range. So it has the same characteristics as the linear function, where our domain is from negative infinity to positive infinity and along with the range. Our x-intercept is still at the origin and same as the y-intercept. So you can see again that for all of these parent functions, the intercepts are going to go through the origin, because again, we're not transforming them and we're not shifting them around. So they're all intercepting the x and the y-axis at the origin. This does not have an extrema. It has a critical point. It has a critical point here, but this critical point here is a point of inflection. The concavity changes from concaving downwards to concaving upwards. So this point here, 0, 0, is a critical point, but it is not an extrema. An extrema is an absolute high, an absolute min, a relative max, a relative min. And since we have none of those, there are no extrema at all. Our increasing interval is from negative infinity to positive infinity. And it does not decrease at all. So from left to right, again, the function is always moving upwards. So from negative infinity to 0, the graph moves upwards. And from 0 to infinity, the graph still moves upwards, as you can see. So it's always increasing. Now our end behaviors as x approaches negative infinity to the left, the function is pointing downwards, so it's decreasing, so the function is approaching negative infinity. And as x approaches positive infinity, our function increases, so it's approaching positive infinity. There are no discontinuities. This function is continuous. And this one is an odd function. Just like the linear function, it's an odd because it's symmetrical over the origin. So as you can see again, if I was to rotate this 180 degrees, flip it upside down, the graph will look exactly the same. Continuing and moving on to our next function, this is the square root function. Our square root functions look like this. They basically look like if it was half of a parabola. So if you have a parabola again pointing this way, half of a parabola will only be this part right there, the positive part, and it's rotated to its side. So it kind of looks like a U, all right? But because we need it to be a function, we don't have this bottom part right there. So this is what the square root function looks like. And obviously the rule for the square root function uses the square root of x. Now this one changes a little bit. The domain of this function is only the values from 0 to positive infinity. And the range is from 0 to positive infinity. Because it only lives again above 0 and to the right of 0. So our domain is from 0 to infinity, so that's that direction. And the range being the y values are from 0 to infinity. And it's a half interval where the first half is closed. Now everything else in terms of the intercept, well not everything else, but in terms of the intercept, it's still the same thing. Our origin is at our Origin is where this graph is going to cross the x-axis and the y-axis. So our x and y intercept are at the origin. This in terms of extrema, there are technically no extrema because there is no turning point. We have a minimum value at the origin 0, 0, but we don't consider that an extrema because it does not change directions. Remember, these extremas are critical points, and these critical points is where the graph is going to change direction. So while we do have an absolute minimum value right here at the origin, we do not normally classify that as extrema. So we're going to just leave it as none because it's not a turning point. Now, increasing and decreasing behaviors. Well, it's increasing from, and it's on its domain, from 0 all the way to positive infinity. Again, since it only exists from 0 to positive infinity, and it's only moving in one direction, upwards, it's only increasing in that situation. So it doesn't decrease at all. Now the end behaviors. Again, since the domain is only from 0 to infinity, x is not going to approach negative infinity. Okay, so it's not going to approach negative infinity, so we don't have to worry about what's going to happen there because this function only exists from 0 to infinity. So our only end behavior is to the right, so to positive infinity and not negative infinity. So let me just erase the negative sign there. And because it's increasing, that's all it does. It only increases. The function again is approaching positive infinity as x approaches infinity. Now, this function is still continuous, even though it starts here and doesn't exist anywhere over here or down here or to the left at all of 0. This function only exists to the right of the origin of 0, 0. It is still considered continuous because this has no gaps, no holes, no jumps, nothing like that. So this is continuous. And in terms of even or odd functions, this is neither. Neither even nor odd. And because it has no type of symmetry, it is not symmetrical through the y-axis. The left side and the right side do not look the same. And if I flip it, I do not get the same graph. Rotating this 180 degrees does not give me the same graph. So this is not going to be symmetrical through the origin nor through the y-axis. Which moves now, let's move on to our next one, which is our cube root function. So like the square root function, it uses the radical symbol, but now our index is 3. So we have now the cube root function, and the graph looks more complete. So it's very similar to the square root function where we have this piece right here. It's a little bit more narrower. You'll see that this is a little skinnier and closer to the x-axis. This is a little bit wider, as you see right there. But it also has the left part of it. So it's a little skinnier than the square root function, and it also has a left parts to it, which means that our domain is going to be all real numbers from negative infinity to positive infinity. Every single one of these points here on this graph is going to have an x value that's going to reach the negative infinity to positive infinity. And the range is the same from negative infinity to positive infinity. Because again, this is going to continue going down, down, down. So the graph will have again y values that are going to reach negative infinity, and it's going to have y values because it's moving upwards so slightly to positive infinity. Our x-intercept is at the origin. Our y-intercept is also at the origin. And again, in terms of extrema, this does not have any at all. No absolute max, absolute min, relative max, relative min, nothing like that. So no extremas. Now, in terms of increasing and decreasing, this graph from left to right is always getting higher. The y values always get higher and higher and higher. So the graph is always moving upwards. So very much like the cubic function, the linear function, this function here is increasing from negative infinity to positive infinity. And because it has no extrema, it's not changing directions. So it is not going to decrease since it's always increasing from negative infinity to positive infinity. And again, no extrema, meaning no turning points, no change of directions. Now the end behaviors, because we actually have the graph approaching negative infinity, we have x coordinates where it's actually approaching negative infinity. This one is going to have a behavior to the left, and that's going to be negative infinity. As x approaches positive infinity, the function approaches positive infinity. So very similar, like I said, to the linear function and to the cubic function. It's pretty much almost the exact same kind of characteristics in terms of the way the graph behaves. It of course just looks a little different, it's shaped differently. And in terms of even or odd, this is again an odd function because of the symmetry that it has. Just like the linear and cubic, this is symmetrical through the origin. Flipping this 180 degrees and again flipping it upside down is going to give me the exact same graph. So this is an odd function because it's symmetry over or through the origin. However you want to say that. You could say it over the origin or through the origin, depending on where you read it, but it means the same thing. And then finally, we have this last one here. Our last parent function we're going to go over is the reciprocal function. The rule for this function is 1 over x. So this function here has some things that are indistinctly different from all the other ones, and we'll start with the domain. Notice that the domain, again, of this graph starts from negative infinity and it goes all the way to 0. Notice that there is a jump here, all right, a discontinuity, an infinite discontinuity there where we do not actually reach 0. So it's going to go from negative infinity to 0. It jumps 0 and then continues from 0 all the way to positive infinity. So here our domain is simply going to be all values of x except for 0, which again means what I just stated, from negative infinity to 0 and then from 0 to positive infinity. But use this notation, again, make it easier on ourselves, and we'll just simply use that notation there. Now the range, same situation. Again, the graph exists down here, so for all of these values of y, and it curves this way, but then it reaches again this plateau and it levels off. Okay, and it approaches again this horizontal line, which is y is equal to 0. It jumps that and then continues moving upwards, well, decreasing in terms of left to right, and it exists right there. But notice that it does not have a value for y at 0. So just like our domain, our range is going to be all values of y except for 0 again, which means simply again that y would be all of the values from negative infinity to 0 and then from 0 to positive infinity. But again, using this notation makes it a lot easier to write instead of writing that long interval there. Now, because we're not touching, our domain doesn't include 0 and our range doesn't include 0, We do not include again this nor this. Okay, let me color coordinate them differently. Let's do this in blue, and then we'll keep the y-axis right here, y equals to 0 or not 0, in yellow. So because we're not including that, notice that the graph doesn't touch the x-axis or the y-axis. So we have no x-intercept and no y-intercept either, because again, it's not part of the domain in the range, so we're not going to be intercepting the x nor the y-axis. In terms of extrema, again, this does not have an extrema, and the reason it does not have an extrema is because it does not change directions. It never increases. This is probably the only graph that does not increase. Notice from left to right, again from left to right, going in that direction. This graph is going downwards. It jumps over this discontinuity, this infinite discontinuity, continues from up here, and then continues to go downwards again from left to right. So it has no increasing interval, and this function only decreases again in its domain. It only decreases from negative infinity to 0, and then decreases from 0 to positive infinity. For this one here, I have no other option but to write the interval like this. I can't say that it's decreasing except at 0. I have to write it again as the interval from negative infinity to 0 and from 0 to infinity. It just makes more sense. Now the end behaviors. As x approaches negative infinity, this is leveling off. The left end again is not pointing again upwards without bound. This is bounded by again our x-axis. So our function is approaching the value of 0. Again, this blue line is y is equal to 0. So it's approaching the y values of 0. And as x approaches positive infinity to the right, is doing the exact same thing. It's approaching 0 because again, it is bounded by that horizontal isotope. This is the only function that is discontinuous. So this function is discontinuous, and this is referred to also. Let me move this up a little bit. Hold on, give me a second. Need some space up here. There. And this function here is an odd function. And again, simply because its symmetry is over the origin. Again, you can see that if I rotate this 180 degrees, flip it upside down, the graph will look exactly the same. This end will be up here and vice versa. So these are the 7 parent functions again that you should be very familiar with, and the characteristics about them. Again, looking at the graph, you should be able to understand again the exact same characteristics, know again where the graph is going to look like, and more than anything else, be familiar with again the parent function and its respective graph. Now, understanding what the parent function and its respective graph should look like again can help you fill out all of this and understand again all of those specific characteristics about each one of these parent functions. Again, thank you for watching. If you do have any questions, please send me a message on Remind, and I hope you have a great day.